Testing. Now it's working. Mic is hot. Let me turn it down a notch. Sorry, all of this stuff that I usually do before class and I did not do. Here it is. Okay, I'm ready now. Okay, so first off, first things first is dealing with, not this, where is it? I had it up there just a minute ago. Now it's lost. Hold on a minute. Maybe if I click this. Huh. Where is this thing? I had it. That's so weird. Did I close? I must have closed my, oh no, here it is. I found it. Okay, I found it. So here it is. There's my adaptive integration. So we can talk about this and talk about strategies. And if you need a couple more days, that's fine. Because I kind of just left you hanging there. So I've got my stuff here. I suppose you could just watch the video and pause at the appropriate places. But I wanted to sort of point out how this all works. They're both pretty much the same, Simpson and adaptive midpoint. But it's the same idea. And then we'll see if you have questions or where I can help you. But here's the general idea. Let me zoom in a bit more, just so you can see what I did. You don't have to do it identical to mine. You don't have to do it. It's fine. But I've got my midpoint rule here. You did the same thing for Simpson. Simpson is almost the same. So you've got your midpoint rule, 2 lines. It's all you need. Now, in order to capture all of the nodes, because I want to know where I'm actually evaluating the function, because that's the cost. The cost of doing integration is actually function evaluations. So I want to know where it is. That's what this is. So I've just set up a list here. Hope it goes well. Go. Okay. Call. It's the president of the United States. Well, could be the president of the college. I don't know who it is. I'm just kidding. But it could be. I don't know if it's job related. No. Hope he gets the job. But anyway, getting back to this. Yeah, he's probably fine. What I did was I defined this thing, and it's a recursively defined function. So if you're having trouble with it, that's probably the deal. Is it's recursive because it calls itself. And so in order to get everything to work, what I did was, and we did this in class, but it was before break. So this is the midpoint. Simpson looks almost exactly the same. Is I have the adaptive midpoint with the function, the 2 endpoints, the old midpoint, which is the well, we'll get to that. And then the tolerance. And then here's where I just add to my list of nodes. So I'm just like, okay, the next node is this one. And that's the midpoint of the 2. I suppose probably I should start, you know what, I should do that, is I should start with A and B. I don't know how to do that, though, because the A and the B are part of this function. I'd have to write a second function. I don't want to do it. So if I had a second function that called this, then I could start off with the L as A and B, but maybe you could make it better than I do. But in general, here's the, let me switch over to, do it on here so that you can see it. Yeah, ignore this. This is Calc 2. So the idea is that you've got, whoa, that's weird. Here we go. You've got your function. There it is. You've got your A and your B. And then what we're going to be doing is we're going to use, just a minute, this is tilted. Let's see if I can fix. It's a little better. And so then what you're going to do is you're going to be pumping this into your function. And so the A and the B, let's just use the trapezoid. Trapezoid is a little bit easier to visualize, even though you don't have to do this. But if we did an adaptive trapezoid rule, what you would do is you would have your old, so that area is going to be the old trapezoid, the old estimation. And then, of course, what you're going to do, split this thing in half and come up with 2 separate. So this is the midpoint of these, A plus B over 2. So this is just conceptually how this works. And then the new one is going to be the area of this plus this. So there it is. So this is, here's the new one. And then what we try to figure out is have we gotten close enough to the truth? The truth, of course, is the actual area under this curve. And so the way we evaluate if we're close enough to the truth is we say how much, what's the difference between old and new? So you do, okay, old minus new, and you say, okay, is that close enough? Now, it depends on if you're using so of course, absolute value, that's going to be an estimate for how close we are to the truth. And it turns out that if you're using Simpson's rule, and you do this, that this difference will be 15 times bigger than how close you are to the truth. So strangely enough, and we went over the proof before break, but it turns out that old minus new is approximately equal to, we could do it that way, is approximately equal to 15 times how close, 15 times the actual error. And by actual error, I mean the actual error with the new approximation. So that's where that 15 came from. We did this, I forget the exact derivation, but it's pretty easy when you look at the actual formulas for the Simpson's rule. So that's with Simpson, so Simpson. With both the trapezoid and midpoint rule, you have this, that the old minus the new is approximately 3 times the actual error. So essentially what you're doing is, here I'll show you this here. So that's where the 3 came from right there. So basically what I do is I take the original, the old one, that's the whole thing. I split the interval in half and I compute 2 new midpoint rules, or Simpson's rules. And then I ask the question, are these 2 minus the old one, the difference, if the difference of those 2 together minus the old one, if it's smaller than the tolerance, that's how close we want to be to the truth, times 3, then I'm all done, I'm good. Otherwise, I have to go through this rigmarole again. So that's all this does. And then the last bit is that every time you do the rigmarole again, you split the tolerance between the 2. So essentially what I'm going to be doing is if it's not close enough, then I do adaptive midpoint another time with the first half, and then again with the second half. But I use those as my old, so it's essentially you're just doing it over and over again. And you say, okay, half of the error can go into the first half of the error can go into the second half, and then I'm all good. So here's what that would look like here. It's like, well, if it's not close enough, then we're going to do it again, and we're going to split this one up. So we got to divide, and we divide this one up, and you can see that this is going to be a big difference here, and this is going to be a much smaller difference. So there's that trapezoid and this trapezoid. And so maybe we'll be all good with this side, but this side is still too far away from the truth, and so we'll just work on refining that side. So that's what the whole point of this is. So that's kind of a general overview, and that's where these numbers come from, the 3 and the 15. So when I did my Simpsons, we did Simpsons in class. So here, the only difference between the midpoint and Simpsons, adaptive Simpsons, is this is 15 right here, and of course, instead of saying midpoint, I'm saying do the Simpsons rule. But that's pretty much it. And then I was a little disappointed with myself in terms of the types of stuff. Where is my mouse here? That I was having you do, and so I wanted to do at least one thing. Let me show you. Where is it? Let's see. I wanted. Where is it? There it is. This one. That doesn't make sense. -1 to 1. Hold on a minute. Why is this? Oh, I see what I've done there. Okay. Let's do negative. I don't understand why it's not. Just a minute. So, okay, just a sec. F2. Oh, that's the sine curve. What's F2? Just a minute. F2. No, F2 is the...
1 over 1 plus x squared.
Yeah, that's the one I want. It's 1 over 1 plus x squared between -1 and +1. Okay, maybe let me do this. Let me print L. I just want to make sure. So this is kind of my output here. Okay, so I've got the sine of x I don't care about. It's this one. This one I care about, the 1 over 1 plus x squared. And I've got my tolerance. I've got 15 nodes. Those are weird nodes. Why are they oh! Sorry. Just realized my error. What is going on? Sorry, I don't understand why the nodes look the way they do. Hold on a minute. Let me, just a sec. This is not, because the nodes should all be between -1 and 1. Oh, I see it now. I blew it. I didn't change this from -1. Okay, now this will work. Okay. Oops, -1. Okay, so the thing on the thing that I uploaded was wrong, apparently. Okay, there's still 15 nodes, but the correct answer is here. So I don't know what happened. But okay, this is much better. Yeah, what I wanted to do was I wanted to graph. I should have had you do this, but I did it, so you can see what it looks like. So these are the actual nodes that, and by nodes, I mean these are the actual function, the points. And it's kind of hard to tell how close they are together because they're kind of scattered up and down. Let me change this just briefly and change this to 1. Here we go. And let's try again. All right. Yeah, they're all, that's evenly spaced. Well, that's boring. I thought that they would be further apart in some areas and closer together in others. What if I change this to just 0.01? That's going to be worse. Let's try this. How many nodes are there? 127 nodes. Okay, let me just see what happens. They're all stretched. Oh, now this makes me worried that my code is wrong, because they shouldn't be evenly spaced, especially with this function is such that they should be uneven. Maybe if I try one more time with a slightly different function. Oh, let's do F1. F1 is a good one. Just a minute. There we go. We'll just do this one, F1. I just want to see, let's see, so from 0.1 to 10, F1 from 0.1, give me a sec here, sorry about this, to 10, and let's just back off a bit. Yeah, I just want to demonstrate the idea that there's 83 nodes, okay. Okay, that's much better. Yeah, see, so just so you can see, these are just along the x-axis. Well, actually, I put the function value 1. But you can see that for this function, this is sine of 1 over x. It didn't need as many function approximations over here. But over here, where the sine of 1 over x goes up and down very quickly, we needed a whole bunch of them. And so that illustrates the adaptiveness. So that's, yeah. So I guess the code is working. I just was expecting more out of it than I wanted or thought I could get. Okay, so what sorts of issues, questions, concerns do you have? I wasn't planning on doing a workshop day today. I mean, if we need to, we could, and I'll just turn off the recording. But is there anything like major that we need to talk about anymore about the adaptive integration, or you think it's okay? I know Sam's fine. So what do you think, Grayson?
The code for adaptive midpoint that I have, it works fine for sine, but when I plug in the other equation, it spits out 0.
Oh, interesting. You just get 0. Well, that may be an issue for me to take a look at individually a little later on, if that's all right.
Mm-hmm.
So yeah, but the sign gives you the correct answer. Yeah. So and you've got the limits set up correctly? -1 to 1. Interesting. Yeah, I'll be interested to see what's going on there. Yeah, let me just think. What could happen? Like just as a what is it called? Like just to think of like what could go wrong. You could, and this isn't. I don't know if this is what's happening there, but let's just imagine that you did, yeah, if you do adaptive integration with the sine of x, here's the sine of x, from 0 to 2 pi. Imagine doing this. Then notice what's going to happen. The very first version of, let's do the, oh, well, this wouldn't be midpoint, would it? But it could still be happening like this. But if you did this with trapezoid, your first trapezoid is this, and you have an area of 0, which is correct, by the way. But then your second trapezoid, look at what happens with the second trapezoid. You get this plus this, which is also 0. And so certainly we wouldn't think that this was close to correct, even though it is. It just by chance happens to be correct. But I guess if I changed my function slightly, let me get rid of this. Let's say I did the absolute value of sine. That's a function. Here's the absolute value of sine. That has a positive area. Whoops, I didn't quite make it to the end there. Let's try again. Hold on a minute. But yeah, the absolute value of sine would look something like this, or sine squared. Okay, that looks terrible, but you get the picture. That if I did the first trapezoid is 0, the second trapezoid is also 0, and you're like, well, 0 minus 0 is 0, I'm good. When you're nowhere near the right answer.
Yeah.
So I don't know if that's what's going on.
That's
it's something.
What happened. I forgot to update the equation.
Oh, okay. Oh, okay. So it's, because sine of x is 0. So, yeah. Okay. Well, that answers that. Anything else? Other technicalities, or just like why do we do this, or anything like that? So I can help you individually maybe later, but yeah, what's going on?
Yeah, I was just understand. So in the disadaptive approach, so it increases the stuff automatically.
Well, that's the idea is that you've got like your adaptive, so adaptive, and you're going to put in your function, your a, your b, and an old estimate, and a tolerance. So this is sort of the what my input is. And then if you're not close enough, if you don't think you're close enough to the truth, then the output would be, so you do some code here, but then if you're not close enough, then you say, okay, we're going to do adaptive for f, and then a plus b over 2. You have a new old, we'll call it m1, and the tolerance over 2, plus this same thing, but with, so you're basically doing this recursively. So that's how it kind of automatically, so it's like a recursive, well, it is a recursive function. It's nothing like anything. It's just the way it is. And then this one, of course, you're going to do the function value from a plus b over 2 to b, and this would be like m2 or something, so that you'd be like, okay, so if you're not close enough with those endpoints, then, well, we're going to split it up. We're going to do this one and say, okay, you can have half the tolerance go there and half the error or the tolerance go there. So yeah, and so it does automatically in a sense, but it's like any recursive, like you've probably written various recursive programs for your computer science classes. It's the same idea. You're just reusing, and you're saying, okay, if this doesn't work, then go back and do it again. And then do it again and keep building on that. Yeah, and so if you get stuck with it, though, I'm happy to come and help you maybe later tomorrow or something. But all right, anything else? Other worries or fears or confusion? All right, so we're going to shift gears, just get an introduction. So we won't have homework for this next thing until Friday, so don't fret. So if you're still finishing up, because I don't think it's due until tonight, and even then, it's not due till I download it and look at it. I mean, to be honest, so it's not really due till whenever, later this week. But we should move on to differential equations. I know some of you saw this on the screen and thought, oh, he's just getting ready for next class. No, I am not. This is actually what we're doing. It's the next topic in our in the typical curriculum for numerical methods. So, but don't worry, today is just a quick sort of very basic introduction into what differential equations are. So to help understand what a differential equation is, we're going to take a look at what's called what is it called? Discrete? Why can't I think of the name? Well, anyway, it's like a discretization of a differential equation in the form of a population growth problem. So let's take a look at two different colonies. You have two isolated colonies of people. These are on islands in the South Pacific or whatever, I don't know. So maybe some hidden valley somewhere that you, so you have colony number one. Colony number one has 100 people, and it turns out that they gain 10 new people each year, constant 10 new people, which is pretty impressive for 100 people. You couple them up, and that's 50 couples. So they're pumping out 10 new babies, maybe, each year. And so I want to know what's going to happen 10 years from now. How many people will be in that colony? And then the other colony that I'm interested in is a colony where there are 100 people, but they're a little bit more conservative, or maybe they're just not as prolific. But instead of getting 10 new people each year, 10 babies, they just increase 5% each year. So 5% new babies each year. Your job is to figure out how many people will be in each of those colonies 10 years from now. I'll let you go ahead and do that. I think you probably can figure it out pretty easily. If you have a calculator, it'll probably be easier for you. So if you don't have one, I have more over there. I have one up here, and we can do this. You can also work with a friend if you need to discuss what's going on. So there's this one. There's many more. Maybe I'll use this one. Whoops, sorry. Clicked the wrong thing. All right, let's see how we're doing. I think it's not that hard, or maybe if it is hard if you have no idea what to do, but I hope you have an idea. Austin, talk to me about colony number one. How many people are there going to be in 10 years? 200. 200. How did you figure that out?
100 plus 10 times 10.
Okay, so it's like this. You say, okay, this year there's 100, and then next year there's 110, 120, 130, and you see where the pattern is going, of course. You know that you get to 200 in 10 years. Beautiful. Well done. Okay, the next one is a little trickier because, well, we'll talk about it in just a sec, but Rachel, what do you think of colony number 2? Do you have any idea of how to figure out, or do you know how many people there will be in 10 years?
I got 162.
Ooh, interesting. Okay, how did you get 162?
So for each, so like first when you add 5, that's 5% of 100, and then you do 5% of that and add that to 105, and 5% of that, add to 110.
Yeah, so herein lies the problem, and curious, I guess you didn't care that there was a decimal number of people.
I had the decimal, it was like
110.89.
162.89.
Yeah, so Yeah, so, here, let me, just a minute. Let me do this on my, I did it where I cared about the decimals. Just a minute. There's nothing wrong, I just wanted to, just a minute, let's see, times 1.05. Okay, so you got 105, then 110.25. Yeah, I guess that's what I'm saying. So you got a fourth of a person there. So you could think of this in one of two ways. One way you could think of it is that there's a baby, but it's not quite gestated all the way, right? So it's still in there, but it's coming. So we're going to count it as a quarter of a person. I don't know. It's too tragic to think of the alternative. So I'll just think of it that way. And then I got 115.76. 25, I guess. And so there again, maybe there's a baby that's on its way, almost there, you know, like it's in the third trimester. And then the next one was 121.55. And where did you end up with 162, you said?
Yeah.
Okay, 0.89. Yeah, 0.89. And so each one of these, you're just multiplying by 1.05, right? So, or 1.05. So another way to think of this, if it bothers you, the decimal numbers of people, then you could, like if you force the integers by just rounding down, then you would get this. Let me see, where are my, I did this, but I need to grab it. Here we go. So on my calculator, I have a function. If you press math, you can choose either round or integer part. I used I-part, which is integer part, which rounds down. So it might actually be better to round the normal way, but oh well. Oh, you know what I could do? Just a minute. Just a sec, let me fix this. I'll round the normal way. I couldn't get the rounding to work, but rounding the normal way would be better, wouldn't it? So just a sec. So entry, and change this to plus 0.5. Okay. So I got 105, then 110, then 116. So rounding the normal way, if you do like multiply by 1.05 and then round the normal way, here's the numbers you get. So it's a little bit fewer numbers of people, but it's, so 128, I'll just dot this, just a minute. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 160, oh. Actually, I got the same answer. Interesting. I thought it would be a little fewer, a couple fewer. But there you go. Interesting. So 163. Okay, but the point is that what we're doing here is we're making a prediction for the future based on some sort of a model, a mathematical model. And this is similar to what we do in differential equations. I think most of you have had differential equations. If not, don't fret. We're going to talk about it right now, differential equations for both of these. When you think of population 1, so maybe I should label these. Give me a sec. Clear. Okay, so population 1, or colony 1, too late. And then this is population 2. Population 2. I'll draw a line. So here are the differential equations for each of these. So for population 1, you have the change in population with respect to time is equal to 10. So we just get an additional 10 people every year. That's what that is. Whereas the population 2 situation is that the change in population with respect to time is equal to 5% of the current population. So there's the differential equations versions of these. And if you've had differential equations, they shouldn't be very difficult or shocking. It's pretty easy to recognize these. Don't worry, we don't have to, well, we're not going to solve differential equations analytically here. We're going to do it numerically. So that's the goal of the next couple of weeks, is to learn how to solve differential equations numerically. Because it's hard to do, like, not numerically. Analytically, it's hard. And some of you know that because you're in the class. But anyway, so it's a difficult thing. So this is just going to hopefully make it easier. Oh, and by the way, here you have P sub 0 is equal to 10 or 100, and here the same thing. P of 0 is equal to 100. So this is the sort of thing we're going to be given. And what we just did is actually a solution technique called Euler's method for solving differential equations. So we just solved both of those differential equations using Euler's method. But we need to formalize this so that you can see exactly what it means. By the way, in terms of these two colonies, it looks like colony 1 is doing better than colony 2 in terms of people. But if you go extend the time horizon a little bit further, you find that colony 2 crushes colony 1 eventually. So you notice that around 30 years is where colony 2 catches up. Colony 2 is red, colony 1 is blue. So around 30 years is where colony 2 catches up with colony 1 and eventually exceeds colony 1. So that's actually the power of compound interest, or the power of exponential functions. You know, a linear function is never going to be better than, in the long run, than a compound or a exponential function. So eventually, it just completely destroys colony 1 in terms of population. Okay, so there's that. Let's see, do we want to talk about baseball? I don't know that we do. Yeah, we will, just briefly. This is an example that I generally will use in differential equations just to justify the existence of differential equations. And that is this. You probably recognize this from your days in high school physics or pre-calculus. Both of those solve this the same way. And the way that you solve this, the way you solve this using high school physics or using pre-calculus, whichever way you want to choose it, is you just assume that this thing is going to be a parabola, right? That's what it is. When you throw something through the air, what do I not care? I don't care if this hits the ground. So when you throw this through the ground or through the air, I'll try to do my best to keep it in front of the screen. You'll see that it follows close to a parabola. So there it is, nice parabola, parabolic arc. And indeed, that was almost exactly a parabola because this thing, these keys didn't ever get moving fast enough for it not to be a parabola. So there is a nice parabola, but in general, when you hit a baseball, it's going so far, so fast, that it's not just the force of gravity that takes hold of it. There's air resistance. And so when you do this, do I have the actual, oh, I don't have the picture. Sad. Oh, no, yeah. So there's actually two differential equations. I don't have the solution. Well, I can tell you what the solution is, that if you take that information and you plug it into the differential equations, so here's what the picture would look like. Whoops, I'll draw it. So the high school physics version would be something like this, a nice parabolic arc, about 836 feet, which is ridiculous. You know, 112 miles per hour, and that's fast, but it's not that fast. And for it to, that's way out of the park, isn't it? What are baseball parks? 450, yeah, 450 is the biggest?
I mean, yeah, that's like center field is 450 usually.
Okay, yeah, so this is no way that anyone hits this.
Yeah, it's crushing.
Yeah, it's crushing it. But this is totally reasonable because this is, generally the ball comes off the bat faster than the fastball. So you get a fastball, 100-mile-an-hour fastball, it's going to come off the bat a little bit even faster. So anyway, I did the math, but in differential. I don't have it here, sadly, but it looks more like this in reality. And not even that. I think it's about a third. Like the actual distance is like 90 meters for this particular problem when you factor in wind resistance, the fact that the ball, so things slow down. So what's happening here is it's like going fine, but then it's like, well, there's actual air that you're moving through, and so things slow down, and eventually it just peters out and drops straight down like a rock. So kind of interesting. I've never actually observed a pop fly from the side, but I'm pretty sure that it's, I mean, at least theoretically, it should look something like that. It's not going to look like a big parabolic arc. Yeah, so in reality, it's more like, if my memory serves me correct, it's more like 96 meters, whatever that is in feet. So that's like 300 feet, 350, which is more reasonable, right? That's like, okay, yeah, whatever, it's reasonable. Okay, so let us go on. Yeah, well, good enough. Okay, so this is, oh, logistic growth. So one more thing, I guess, and then we'll, why do I have all these models? Oh, the next one is finally Euler's method. So one more model that you might have seen in your differential equations class, or maybe if you've never had differential, here it is. Logistic growth, what that does is, as opposed to unrestrained growth, which is what this is like unrestrained exponential growth. Logistic growth takes into account the fact that there is some sort of a maximum carrying capacity, and in this case, the carrying capacity is equal to 500. So whenever you, and the way to think of this is if the population is more than 500, then this piece of this differential equation turns negative. And so that means that the slope, P prime is the slope will be negative, meaning people are dying. So if you ever have too many people, or too many hermit crabs, or whatever population you're observing, bacteria, for the environment, you end up losing. People start dying. I'm not going to do this one. You could do this yourselves, but it's going to be a very similar situation where you can map things out, starting at 100. So this could be colony 3 maybe. But what you find with a logistic growth model is that things increase roughly similar to your exponential growth until you get to about halfway towards the carrying capacity, and then things start to taper off. And so this is the carrying capacity here. So you end up with something like this, where population increases and levels off. Not that important. I guess, I don't know why I have so many examples here. I'm trying to justify why we care about differential equations. There's lots of models. Trying to predict the future, you're trying to predict stock prices, you're trying to predict weather. All of those things involve differential equations. Trying to say, oh, well, there's this, and I want to know what's happening over there. And so let's take the data, the thing that we're looking at here, and say, let's see if we can predict what will happen in the future. Okay, so let's get to the method, finally. The method, and we will practice this, and we'll put it into the computer on Wednesday. But for now, we'll just sort of talk about it, and then we'll have homework due on Friday, because that way you can clean up your adaptive integration business. So Euler's method is the simplest version, the simplest thing that you can do to solve this. It is not the best, but it is the simplest, and so it's easy. So here's how this works. This does exactly what we've been doing. What you do is you have your differential equation. Why is it u? I don't know. So u prime is equal to some function of u and t. And you have an initial condition. So this is the initial condition. I'll show you an example here in just a minute. Initial condition. Ooh, that example I don't like at all. I'll do it. Sorry, I'm looking ahead. I see the example. I don't like it. But anyway, we're going to do exactly what we did back here with colony 2 in particular. Colony 2 is a great example of Euler's method. Euler. Because what we did was he said, okay, how much of an increase can we expect? And we're just going to do that increase incrementally each year. I guess the same thing happened here, but this was exact, so it's not as exciting. So that's what this is. Next year will be this year plus however much increase you get from your differential equation. So the differential equation is how much increase to expect, and then this delta t is how much into the future you're going to go. Back here we were counting by years, weren't we, with the colonies? Yeah, each year. So we did each year, but we could have gone by half years, do 6 months at a time, in which case this wouldn't be very exciting. You'd have 100, then 105, then 110, etc. This one would be a little bit more interesting. Start with 100, and then you'd have 102.5, because you're going half a year, and half of a 5% increase is 2.5, and so on. So that might be more interesting, be closer to making a good prediction for the future. But that's what that delta t is. That's the step size. And as you can imagine, the smaller we make the step size, the closer we're going to be to the truth. So let's actually do this with that differential equation, which I don't like at all. Just trying to decide if I want to switch. I'm not going to switch. I don't like it. I'll just leave it. I'll leave it. We'll do another one here in just a minute. Here's what I'll do is I'll copy this so I can do it on Notability and do a second one. Yeah, this one's terrible. Sorry, but well, okay. The only reason why I don't like it very much is because I don't know what the real solution is. So I don't know what the truth is. It'd be nice to know what the true solution was, so we can compare. And this one, that's not linear. That's not. I don't even know what to say about that. Yeah, it's not separable. I don't know. Maybe I could use. Yeah, there's probably an identity I could use. There's a sum identity, but I don't want to deal with it. So I'm just going to go on and do this. So give me a sec. Put this in here. There it is. We'll do this one, and then we'll do a better one over here. So this will be for the better one, and for the better one, I am going to get rid of, there, get rid of that differential equation. There. So I'll make up a new one in just a minute. I'll make up one that is better. But that's okay. Well, this is good, a good example of how we use numerical methods to solve differential equations. So we start off with y of 0 is equal to 1, which means when t equals 0, y is equal to 1. And then we want to predict the next step. Now notice that I have delta t is 0.5, so that means that I'm counting by 0.5s. And that's why I have 5 rows. So the t, you know where that's going. It's going to be nice regular all the way down. Now let's go ahead and pull out our calculators because it's the only way we're going to be able to do this, sadly. So essentially, I want to know what is the growth rate. It's like on the like how many more people will there be if this was a population, but it's not. But what is the rate at which this is changing? And the rate at which it's changing is the sine of t times y. So you're taking the product of these, computing the sine, and you get the rate of change. Well, it turns out that the rate of change for this first one is easy. It's just 0. So if there is no predicted change for that particular step, then of course the next y is going to be just 1 as well. I better write down, here I'll write down the Euler's method, that yi plus 1 is equal to the old yi, plus the slope. How am I going to write this? I guess I'll write it this way. F evaluated at t sub I, y sub I, times delta t. Something like that. I think that's approximately what I had written. I think it was in a little different order, but this will work. So just so to orient you, you have the next step will be the old step plus the direction you're going times how far you're going. Okay, so the next one, okay, we've got 0.5 and 1, and here I don't know the sine of 0.5, so I'm going to have to use my calculator. Sine of, so notice what I'm doing is I'm taking 0.5 times 1, plugging it into here, 0.5, and that gives me 0.47. How many digits do I want? 479. We'll just go with 3 digits now, but of course if you have a computer you can go with 20 digits or whatever that gives you. Okay, so then we're going to pump this stuff into here to get the next y. So let me do this one, and then you're going to do the next one. So let's see. This is going to be the old y, which is 1, plus this slope, 0.479, times the step size, which is 0.5. How far are you going? 0.5. And that gives me 1.2395. 1.24, I guess. Since I'm rounding, it would be 2395, but I'm going to round it up to 240. I'll just leave it like that. Okay, so your job is to get the next two steps. So you're going to compute the slope, which is this number, and then you're going to pump the whole thing into this to get the next y value. So see if you can do it yourself. That way you can check to see if you know what's going on, and if you don't, that'll be time for us to discuss. Wow, 141, and Sam's still not back. Guess he'll be watching the video. All right, let's see how we're doing. Zane, do you know what the slope is for this one right here?
I'm doing it right now. My calculator's dead, so I'm trying to input it in my phone.
Oh no, okay. Do you have a sign on your phone?
Yeah.
All right, well, give it a go there. Or you can always borrow one of my calculators. Well, next time.
Is it 0.945?
Sounds good to me, or round to 0.946. So 0.946 we'll go with is the slope. So that's the slope, and now we need to just add that in, but we're going to remember we're just going for a step of 1/2. So take that, multiply it by 1/2, and add it to that. So I'll do it also just to make sure that we're all on the same page. All right, let's find a rando to help out here. There we go. Grayson, did you find the next, so what's the next y value?
I got a different thing for the sign before.
Oh, are you set
I
to?
did more decimals, but it's much different, so I'm trying to figure out.
Are you in radians or degrees?
Let me check. I'm in radians.
Weird. What number did you get?
I got 0.5809.
Weird. And you did the sine of 1 times 1.24?
I did the sine of 1 times 1.2397.
Okay.
Something.
Should be the same.
But I don't know what went wrong.
Sine, we'll do it again, 1.2397. I'll do it up here. I got
It's,
0.9.
yes, I don't know what happened.
Oh, it worked this time?
It might just have been a user error
Yeah,
calculator.
I know.
Off with it.
It happens. So you're going to go ahead and multiply that out and get your new y value.
Just give me like.
Yeah.
So 1.7125 sound about right?
Sure. So we'll just round it to 1.72. So very good. There it is for the next. Now we need the one more step. We're almost there. Matthew, do you know how to get the next slope? So the sine, what am I going to plug in there? Or what did you get for this number right there?
I have not yet calculated it.
I'm sorry, your calculator doesn't work?
I have not yet calculated it yet.
Okay, but what would I do? Tell me what to type into my calculator then.
Multiple of that.
So what am I multiplying?
So 1.5 and 1.72.
Excellent. So you're going to multiply 1.5 and 1.72, and then what do I do with the product?
Put it in the sum.
Into the sign. Very good. So I'll do that for you because I know you're using a phone calculator, which is tragic. But remember, you can always borrow one of my calculators if you need to. So I got, when I did all of what you wanted me to do, Matthew, I got 0.533, I guess, after I round. So 0.533. And of course, you know, if we're rounding it slightly differently, then we'll have slightly different numbers, but it won't be vastly different. And so when we get to Python and we do this, of course, we're not going to, well, we'll round it whatever 10 or 15 digits, whatever Python is set up for, we'll use the maximum number of digits. We won't be rounding, at least not, we won't be. Okay, one more. Oh, actually, no, we're almost there. We just have to get this final number. What time is it? Oh, it's almost time to go. All right. Oh, who's left? Let's see, Eli's left. Eli, what do you get, or how do you get that last approximation?
You take half of the 0.533 and add it to the other.
Okay, so you start with the 1.72. I'll write it out here. And then you add half of 0.533. Very good. So let's see, 1.72. So take the previous answer and add half, because we're doing these little baby steps, times the slope, 0.533, 1.98, 1.99, I guess it is. And that's sort of the target. That's like, well, that's my prediction. So, you know, one way to think of this is we're trying to predict the future. We're sitting here and we're trying to predict what's going to happen 2 years from now. Well, here's where we are. We predict in 2 years, this is where we'll be. I don't know what this represents, but that's my prediction. So apparently, we don't have time for one that I know the answer to, but we'll have to do it next time. Yeah, what we'll do is I have, let's see, dy over dt is equal to 0. Let's see, I just pulled one out of here, 0.2 times t times y. So we'll do the same thing. And t of 0, where is t of 0? Oh, and t of 1. I see what's happened. Not t either. Okay, so we'll do this one next time. So if you don't write it down, that's fine. But that's the one we'll start with, and we'll use delta t, and we'll predict. I don't know. I'll figure out what we're predicting here in a bit. But we'll do the same thing. And this one I actually know the solution to because it's a nice, easy differential equation. All right, well, thank you. If you're stuck on the stuff that you're supposed to do on Python, please do either stick around or come see me tomorrow. So